projects. In this video, we are going to explain about the project entitled as Analyzing V Sentences in Scientific Writing to Predict Peer Review Outcomes. So before getting into the video, let me give you the brief explanation about the project. This project explores how the use of V sentences in scientific manuscripts influence peer review outcomes by analyzing the frequency, structure, and rhetorical functions of first-person plural statements. The study aims to uncover stylistic patterns linked to acceptance or rejection. Using NLP techniques and machine learning models, the project evaluates whether these linguistic features can serve as reliable predictors of peer review decisions. The findings aim to help researchers improve writing clarity and strengthen their chances of publication. Coming to the abstract describes a project that analyzes how authors use V sentences statements written in the first person plural in scientific papers and whether these patterns can help predict if a paper will be accepted or rejected during peer review. It highlights that the study looks at how often the sentences appear, how they are structured, and what rhetorical purpose they serve. The project applies linguistic analysis, NLP techniques, and machine learning models to understand how an author's writing style and tone may influence reviewers. Overall, the abstract suggests that the findings can help researchers improve their writing to increase their chance of publication. Coming to the existing system explains that current models used to predict peer review outcomes mainly focuses on board factors such as writing, quality, novelty, methodology, and traditional linguistic or structural features. Although these approaches analyze elements like sentiment, citations, and readability, they do not pay attention to deeper stylistic choices made by authors, especially the use of V sentences, which play important roles in explaining methods, contributes, and results. Because of these oversights, existing prediction systems miss subtle writing cues. They may influence how reviewers perceive and evaluate a manuscript. Coming to the proposed system or base paper work, the proposed system focuses on using V sentences as a meaningful linguistic features to improve the prediction of peer review outcomes. It uses NLP techniques to identify and classify the sentence based on their purpose, such as presenting claims, describing methods, or interpreting results, and feeds this information into a machine learning model. By combining these rhetorical patterns with standard manuscript features, the system aims to achieve more accurate predictions and offer useful feedback to authors. Overall, it helps researchers understand how their writing style may influence reviewers and supports them in improving their manuscripts for better acceptance chances. Coming to the dataset, the project uses two datasets. They serve different but complementary purpose. First, peer read dataset. The peer read dataset provides scientific manuscripts along with their peer review decisions and reviewer comments, making it highly suitable for analyzing writing patterns, such as the use of V sentences and predicting acceptance or rejection outcomes. It contains thousands of papers from major AI and NLP weights, offering rich linguistic and structural information. Next, we have ASAP dataset. In contrast, the ASAP dataset contains of 10 of thousands of restaurant reviews annotated with star rating and accept level sentiments. Although it is not related to scientific publication, ASAP offers a well-organized large-scale text dataset that is useful for training and testing NLP models, especially for sentiment analysis and feature extraction. Together, these datasets support both peer review prediction tasks and broader linguistic model development. Coming to the novelty or extinction or enhancement or improvement. First, we have done Electra-based embedded extinction. This extension introduced a more advanced embedding techniques using the Electra language model, which significantly improves the system's prediction performance. By applying Electra embedded, to both the peer read and ASAP dataset. The model achieved high accuracy levels, 96.3% for peer read and 89.9% for ASAP, surpassing the earlier models. This demonstrates that Electra captures deeper contextual and systematic information, making classification more precise. Additionally, all existing and newly proposed models were implemented and compared to show the performance improvement clearly. Next, explainable AI integration. To make the predictions more transparent and trustworthy, explainable AI techniques such as line and shape were integrated into the system. These tools helped identify which words, features, or linguistic patterns contribute most of the model's decision. By visualizing feature importance, the system becomes easier for researchers and users to interpret, ensure that they understand why a text was classified into a particular way. Next, a user-friendly web interface was built using Flask to make the system accessible to non-technical users. Through this interface, users can input any text and instantly receive prediction results such as acceptance, likelihood, or sentiment classification. The interface also displays topic modeling outputs directly on the results page, allowing users to analyze key themes in their text. This extension improves usability and demonstrates the practical application of the system. Coming to the flow of the work, first, we need to import the packages. This module loads all required Python libraries for pre-processing, NLP embeddings, and model training. It ensures that every subsequent component, from text cleaning to model deployment, has the necessary tools available. Next, data preparation. In this module, benchmark datasets such as peer read and ASAP review are collected and converted into a standardized format with fields like title, abstract, and body text. All individual files are merged into a main dataset separating accepted and rejected papers for classification task. Next, data cleaning. This step removes noise such as latex commands, citations, URLs, and special characters to improve text quality. The clean text is normalized to lowercase and segmented into sentences using NLP tools like Spacy for accurate downstream processing. Next, V sentences extraction. Here, the system identifies sentence containing first person plural pronouns like we, are, and us. Three variations of the datasets are created. The full dataset, a dataset of only V sentences, and a weighted dataset where V sentences are given higher importance. Next, feature representation. This module converts text into numerical form using TF-IDF and advanced transformer embedding such as BRAT, DCG birth, SCI birth, and long former. Tokenization is performed accordingly to model requirements to ensure proper input formatting. Next, model training. Different machine learning and transformer models are trained, including SVMs and TF-IDF and fine-tuned transformer models. Electra is also fine-tuned as an extension to achieve higher accuracy. Next, hyperparameter settings. Common training parameters such as the add and W optimizer, a learning rate of 2E5 and 5 to 10 epochs are used. This setting helps stabilize training and improve model performance. Next, model evaluation. Each model is tested using metrics like accuracy, precision, recall, and F1 score to assess effectiveness. Confusion matrix and classification reports are analyzed to understand strengths and weaknesses. Next, model comparison and evaluation. This model compares the results of all models and dataset configurations. It highlights which approaches perform best and how V-sentence weighted or transform embedding impact prediction quality. Next, Flask deployment. A Flask-based web application is developed where users can input text or upload files for prediction. The app pre-processes the input, applies embedding, predict the classes, and display results along with topic modeling outputs. The algorithm used are BOWTF plus linear SVC on variance, TF count on whole, TF count on V only, TF IDF on weighted. EXP EI weighted implementation plus SVM, fine tune models, DGC birth, SCI birth, long former, and BRAT. As an extension, we have used fine tune Electra model. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consist of operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consist of application framework Anaconda, primary language Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3, technologies which we use to build the front-end are HTML, CSS, JavaScript and Bootstrap 4. To execute this project, first we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are the model files which contain algorithm information which will be loaded into the project code during the runtime. .ibynd file. This is a Jupyter Notebook files which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Now, coming to the project execution, firstly, you need to copy the path of the code folder from the address bar of a file explorer. Then, open Anaconda prompt. Using the command cd followed by a space, then paste the copied path. This command is used to change the current directory to the code folder's path. Now, compile the app.py file using the command python space app.py in the Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link provided by the framework and paste it in any web browser. I prefer Chrome, so that the home page of the project should now be displayed in the browser. This is a front-end built using the Flask framework. In this page, we have Home button and Register button. Now click on Register button so that the logon HTML will be opened. Here, we need to give the details and create an account for user authentication like username, full name, mail ID, mobile number, and a strong password. Again, click on Confirm Password. Now click on Sign Up so that all the given details are stored in signup.db and the login HTML will be opened, where you need to access the application by username and a password. Now click on Sign In so that the prediction page has been displayed. In this page, we have Analysis button, Data Visualization button, Notebooks button, and Logout button. Firstly, click on Analysis button so that the paper acceptance prediction will be opened, where you need to enter the paper abstract or text below to predict the model. Enter the paper abstract or the text, then click on Predict so that the predicted button will pre-process the input and output is predicted as rejected. And we have the top keywords for the rejection like rule, confidence, redundance, set, antecedent, bias, support, closure, implication case. And we have the prediction confidence percentage and acceptance probability. We also have the analysis summary given here for the rejected reason and the probability of breakdown and the recommendations. Now click on new prediction so that we need to give the new paper abstract or the text. The given input is pre-processed and the output is displayed as accepted. The top keywords for acceptance is near, language, data, protection, system, NN, target, approach, word, and English. We have the prediction confidence and the acceptance probability, and we also have the analysis summary for accepted reason, probability breakdown, and the recommendation. Now click on view analytics. Now click on data visualization. So as we are using two different data sets, we have two different graphs. So first, let us check with ASAP dataset graphs. First, we have distribution of text lengths graph. This graph shows the distribution of text length in the dataset measured in number of words. Most documents fall within the range of roughly 4,000 to 10,000 words with a strong peak around the mid-range. A smaller number of text extend beyond 15,000 words, indicating the presence of a long tail distribution. Next, we have distribution of labels graph. This bar chart shows the number of accepted and rejected papers in the dataset. Accepted papers are noticeably higher in the count compared to rejected ones, indicating a class imbalance that models must account for. Next, we have overall word cloud of all clean text graph. The word cloud highlights the most frequent used terms across all papers. Words like model, use, method, algorithm, and section appears prominently, reflecting common themes in scientific writing. Next, we have confusion matrix graph. The confusion matrix presents how well the Electra model distinguishes between accepted and rejected papers. It shows high true positives and true negatives with relatively few misclassifications, indicating strong overall performance. Next, we have accuracy comparison graph. This bar graph compares the accuracy of different models and dataset variations. Electra achieves the highest accuracy, clearly outperforming both classical ML models and other transformer-based systems. Next, precision graph. The precision graph shows how accurately each model predicts the accepted class. Electra again leads with the highest precision, meaning fewer false positives compared to other models. Next, we have recall graph. The chart displays recall scores indicating how well each model identifies true accepted papers. Electra reaches the highest recall, demonstrating strong ability to capture positive cases. Next, F1 score graph. The F1 score comparison combines precision and recall to show overall model balance. Electra achieves the highest F1 score, confirming it as the most effective and reliable model among all evaluated. Next, we have line feature importance for class rejected graph. This bar chart shows which words most influence the model prediction towards rejected class. Red bars indicates words pushing the prediction towards rejection, while green bars push it away. Larger magnitudes represent stronger influence on the final decision. Next, we have top 20 important tokens graph. This chart displays the tokens with the highest average absolute Sharpe values across the dataset, indicating their overall importance in model prediction. Common words like a, the, and have highly influenced due to frequent appearance and contributes the model decision. Now, let us check with pure read dataset graphs. First, we have distribution of length graph. This histogram shows how long the documents in the dataset are measured in word count. Most texts fall within a lower to mid-word range, with only a few very long documents creating a long right tail. Next, distribution of labels graph. This bar chart shows how many samples in the dataset are labeled accepted versus rejected. The dataset is imbalanced with more accepted papers than rejected ones. Next, we have overall word cloud of all clean text graph. The word cloud visualizes the most frequent terms appearing in the text of the papers. Larger words indicates higher frequency, highlighting common themes in the data set. Next, we have confusion matrix graph. This matrix shows how well the Electra model classified papers as accepted or rejected. The high values on the diagonal reflects correct predictions, while off-diagonal values indicates misclassifications. Next, we have accuracy graph. This bar chart compares the accuracy of various ML models. Electra shows the highest accuracy, while Longformer performs the lowest. Overall, the most models fall in the 0.65 to 0.80 accuracy range. Next, we have precision graph. The precision chart illustrates how well each model avoids false positive. Electra again leads with the highest precision, whereas Longformer significantly underperform compared to the others. Next, we have recall graph. This graph compares how effectively each model captures true positives. Electra maintains the best recall, while Longformer records the lowest, indicating it misses many irrelevant cases. Next, F1 score graph. This bar chart compares the F1 scores of different ML models used for classification. It highlights that Electra achieves the highest performance, while models like Longformer lag behind. The visualization helps quickly access which models are more effective. Next, we have line feature importance for class rejected graph. This chart shows which words contributes most to predicting the rejected class using line. Red bar indicates negative contributions towards rejection, while green bar shows positive influence pushing the prediction away from rejection. It reveals which tokens most strongly shape the model's decision for this class. Next, we have top 20 important tokens graph. This horizontal bar chart represents the top token ranked by their average SHAP values, indicating overall influence on model prediction. Common words like a, the, and appear highly important due to their frequency presence. It helps interpret which tokens broadly driven the model's behavior. Then click on logout. So finally, this project demonstrates that analyzing V sentences provide valuable theoretical insights that significantly improve peer review outcome prediction. By combining traditional manuscripts, features with specialized V sentence analysis, and advanced transformer models like Electra, the system achieves high accuracy and interpretability. The integration of XAI tools further clarifies which linguistic cues influence decision, while the Flask interface makes the model accessible for real-world use. Overall, the approach enhances both predictive performance and authors' understanding of effective scientific writing. This is all about your project. Thank you.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.